Okay, so in this lecture we'll cover this concept of geometric isomers and also review what a pi bond is and introduce this concept of pi star, anti-bonding, orbital. Okay, so if you remember how pi bonds are formed, so to make a pi bond, so you need p orbitals on adjacent carbons, and then those p orbitals each has one electron in them, and those p orbitals are close enough to in space that they can overlap side to side. So if we had a molecule like ethylene, so if you remember, one of the lines is representing the sigma bond. That's from the sp2 orbital of one carbon overlapping the sp2 orbital of the other carbon. Right? If you review those lectures over sp2 hybridization, then the sigma bond is formed by the two sp2 orbitals overlapping end to end. So that's a sigma bond, and the other line is representing the pi bond, and that's formed by a p orbital overlapping a p orbital side to side, right, like depicted here. Or in terms of the models, right, that would be a pi bond, where this p orbital can overlap this p orbital, and this p orbital, well, the top of this p orbital can overlap, and the bottom of this p orbital can overlap side to side. Or in reality, what it would look like is that where the p orbitals are close enough in space that they can overlap side to side, top and bottom, and that top and bottom overlap counts for one pi bond. Okay, so why are the orbitals, why is one of these lobes green and one of these lobes red? So this gets back to kind of quantum mechanics, is that electrons have wave-like properties. And so if we had a wave, so if we had a wave, then part of that wave is positive, and or in this area the wave would be negative. And so that's what this is, the color of the orbitals is trying to represent. Sometimes when you see p orbitals drawn, you see them drawn like this, where one side is shaded and one side is not, and that's trying to represent the positive phase of one of the lobes and the negative phase of the other lobe. So when you make a p orbital, so you're basically taking two p orbitals from two different carbon atoms, and when you do that, so the two p orbitals could both be in phase, or the two p orbitals could be out of phase. So then when you let them overlap, to form a pi bond, so in this case it's just an atomic orbital. So it's a p orbital on one carbon atom, atomic orbital, and a p orbital on another atom, atomic orbital, and it could be like this or it could be like that. And so then you let them overlap. So they could either be in phase when they overlap, or they could be out of phase when they overlap. So when they overlap, then they form a pi bond if they're in phase, and they form what's called pi star, or anti-bonding orbital, if they're out of phase. So this is bonding in phase, and this is anti-bonding if they're out of phase. So whenever you construct, so you're constructing what are called molecular orbitals. We're taking atomic orbitals, and we're constructing what are called molecular orbitals by letting atomic orbitals overlap. So if they're in phase, then you get constructive interference, or it could, sometimes it's depicted like this. The new molecular orbital extends over both carbons. So that's what's referred to as the pi bond, or if they're out of phase, then you get that. Well, actually what you get if they're out of phase, so that's the carbon nucleus. If they're out of phase, then you get destructive interference, and you get that, which is what's called a pi star, or an anti-bonding orbital. So pi is bonding, and pi star is anti-bonding. And we have two electrons, and so where are the two electrons at? Well, they prefer to be, so this, in terms of energy, pi is lower in energy than pi star. So both electrons, so a molecular orbital, just like an atomic orbital, can hold two electrons. So both of the electrons are going to be in pi. So either depicted like that or depicted like that, or sometimes arrows are used to represent electrons. So arrow up and arrow down, if you remember that from General Chemistry 1, they can have spin 1/2 or spin -1/2. So that would be the arrow up or arrow down. So both electrons are going to be in pi, because pi star is higher in energy. You can make the electron go to pi star, but to do that would require energy. So if you shine light, for example, or you heat it to a very high temperature, then you can get one of those electrons to move to pi star. And that has consequences, as we'll talk about in just a minute. Okay, so the significance of the double bond is that because of the double bond, you don't have free rotation around the carbon-carbon bond. Because if you just take that and rotate 90 degrees, then you no longer have a pi bond, right? Because this p orbital doesn't overlap with anything, and this doesn't overlap with anything, and so forth. And so that requires too much energy to rotate around that pi bond, because you have to break the pi bond to do so. So that molecule is static. It doesn't rotate around the carbon-carbon bond. So this has consequences. For example, if you had this molecule versus this molecule, so those molecules are isomers of each other, but they're not constitutional isomers because the order of attachment of atoms is the same, right? It's chlorine, carbon, carbon, chlorine in both cases. So they're not constitutional isomers, but they are different molecules. They are called stereoisomers of each other. All right, so if I build this right quick. So if we had two chlorines here, so and this will be the molecule on the left, and that cannot convert to the molecule on the right because that requires you to break the pi bond to do so. So you can make this molecule, or you could make this molecule. Right, and they will not convert between each other because of the rotational barrier between the carbons. So you can make both molecules, stick them in their own vials, and they will not convert between each other. And so the two molecules are different. So they are stereoisomers because they differ only in spatial arrangement of atoms. So any two molecules that only differ in the spatial arrangement of atoms are called stereoisomers. More specifically, these are called, so a subcategory of stereoisomers is what's called geometric isomers. So this one's what's known as the cis isomer, and this one is what's known as the trans isomers. And so in the next chapter, I think it is, or maybe chapter 3, we'll look at how do you classify cis and trans, but in general it's pretty easy. If you just split the double bond in half and assign priorities based on molar mass, chlorine's got a higher mass than hydrogen, and chlorine's got a higher mass than hydrogen, and the ones are on the same side, so that's cis. Cis are same. Here, if we split the double bond in half, one's on top, two's on bottom, but on the other side of the double bond, two's on top and one's on bottom, so the ones are opposite, so that's trans, right? Trans meaning opposite. Okay, so cis and trans are examples of stereoisomers. More specifically, they're examples of geometric isomers. And again, they can't interconvert between each other because the pi bond prevents the rotation. But you can make it rotate if you go to a really high temperature, but that may require a high enough temperature that may decompose the molecule. Or what you can do instead is you can shine light on a molecule, because if you shine light on a molecule with a double bond, then that will cause, if it's of the white wavelength, the white frequency, that will cause an electron to promote from pi to pi star. And now that weakens the bond, because now you put an electron in an anti-bonding orbital where there's no constructive interference between the p orbitals. And so in that case, it's possible, if you shine light on it, it's possible to rotate around the double bond. And this is significant because that's the whole basis of how vision works. So in your eye, you have molecules with double bonds in them. And when light hits your eye, it causes an electron to promote from pi to pi star. That weakens the double bond and allows the molecule to rotate, to go from a cis to a trans isomer. And that gives an optical signal to the brain. And then your body has an enzyme that will convert the trans isomer back into the cis isomer, and then it's ready to absorb light again. So that cis to trans interconversion in a molecule in your eye, rhodopsin, is what is the whole basis of molecular vision. But in general, without high temperature or light of the right frequency or wavelength, you can't rotate around carbon-carbon double bonds, because you have to break the pi bond to do that. Okay, so these geometric isomers have lots of consequences biologically. So if we go back to this molecule at the very top, so this is a molecule called tamoxifen. And so it's an important molecule biologically, because the cis isomer has anti-cancer properties, and the trans isomer has no. Anti-cancer properties. So the two molecules, they just differ spatially, right? If you notice, the two molecules, this side of the molecule is the same as this side of the molecule. But here, these two groups have been flipped. So they differ spatially and nothing else. So they're a form of stereoisomers. More specifically, they're another example of geometric isomers. And so stereoisomers have huge consequences biologically. One stereoisomer may be useful physiologically, may have useful properties, like in this case, tamoxifen is something that you get people with cancer can get at a pharmacy to try to treat their cancer. The cis isomer has anti-cancer properties, but the trans isomer it only differs in rotation around that carbon-carbon double bond to position things different spatially. Of course, they're different molecules. They would have to be synthesized separately and isolated separately. But if you administer the trans isomer, it has no biological activity, no anti-cancer properties anyway. So in general, stereoisomers, one stereoisomer may simply be not useful, or it could even be toxic or deadly. So stereoisomers is a huge concept in organic chemistry that we'll talk a whole lot about as we get into other chapters. Okay.